Okay, so now that we've done quartiles and percentiles, we're going to start talking about a 5-number summary. And this is going to really just be using those quartiles again. So remember I said that we had that minimum and maximum when we were looking at the calculator. Well, that minimum and the maximum, this is where they become important. So the 5-number summary of a data set consists of your median, your first quartile, your third quartile, your smallest value, which is your minimum, and your largest value, which is your maximum. And generally, we'd like to arrange these in order from smallest to largest. And the reason we do that is that we want to arrange this data from smallest to largest because we're going to make what's called a box plot with this data later. Also, when we do a 5-number summary, if I was not labeling this, so as an example, that data that we had on the number of classes we were taking, we had a minimum of 0. We had a first quartile 1.5, median 2.5, third quartile of 4, and a maximum of 6. So sometimes we say, hey, here's my 5-number summary, but we don't label the data. So you might just see the 5-number summary listed like that, and we don't list it necessarily as minimum, Q1, Q2, Q3, and maximum. So just be prepared if you're given a 5-number summary, you may not have labels on it. But it's always assumed your smallest number is going to be your minimum, your second smallest is your Q1, your third smallest, I guess, is your Q2. Then the next one is going to be your Q4, and then the largest value you have is going to be your maximum. So remember that data is splitting everything into equal fourths. So if you go back to this data that we did on rainfall in Los Angeles in February, I have a minimum here, I have a maximum here. This is my first quartile. Lost this place, there we go. This is my first quartile, and I just lost it here in the day, there we go. And that's my Q3. So what it's telling me is that between here and here is 25% of data. Which that one's going to make sense. 25% of values are inches of rainfall, or February's. 25% of February's have 0 to 0.92 inches of rainfall. But it also means that this is also another 25%. Sorry, it's like I couldn't get that written in there. So 25 between 0.92 and 3.12 inches of rainfall. And like I said, this is another 25%, but this one at the end is another one. So that's also telling me I'm at that maximum 25% of February's. I thought it was up to 16, but I guess I was wrong. February's have 9.89 or 4.89 to 13.68 inches of rain. So where we knew like the middle values, kind of splitting how that was splitting things up, it's giving me this range now at the end. So I can say between 0 and 0.92 inches of rain, that represents 25% of my February's, where another 25% of my February's have between 4.89 to 3.68 inches of rain. So those maximums are nice because instead of saying 25% is over 4.89, I can put a definitive into it. It's actually 25 between 4.89 inches and 13.68 inches. Okay, and then once again, to show you on the calculator that it was that, like I said, you had that min X and that max X, that was your minimum maximum, that one bar stats. Also to point out here, notice that these Q1, Q3 don't quite match what we did by hand. Like I said, that's because there's sometimes a little discrepancy between what the calculator calculates those quartiles and how we calculate them. So part of the reason we care about your 5-number summary and we care about quartiles is because one of the things we're going to look for is outliers, and then we're also going to make some graphs. So an outlier is a value that is that's considerably larger or considerably smaller than most of our data. So if we go back to that rainfall, like I said, this was like my first quartile. A value like 13.68 might be kind of large compared to the rest of it. Oops, trying to find that little, there, go. There. If you look at it like this, we see most of my value is centered here, and then we have these values out here that get farther and farther away from each other. So when we're talking about outliers, we're talking about the data like we have down at this end, which is considerably further from where the rest of it is kind of clustered together. So anything that's very far from that cluster is what we would consider to be your outlier. Just trying to put 33 in, it's not letting me do it. Let's put in 31, there we go. All right, so some outliers result from errors. For example, a misplaced decimal point might cause a number to be much larger or smaller than other values in your data set. Sometimes when we're trying to record things, like the recording device might have an issue and it records things like, especially temperatures, but sometimes it has a hiccup and then it starts recording temperatures like extremely hot or extremely cold when they're not. So sometimes you got to look at data and decide, is that outlier like caused by an error, or is it really in there because it is reflecting a fact about our population that contains some sort of extreme values? So in the case of the rainfall, there just sometimes are, especially when we have like things like El Ninos and El Ninas and things like that, will have big effects on weather patterns. That could cause you to have outliers that are actually not errors, they're just part of what the data looks like. So this is the temperature in a downtown location is measured for 8 consecutive days during the summer. So remember, this is summer temperatures. The readings in Fahrenheit are 81.2 degrees, 85.6, 89.3, 91 degrees, 83.2 degrees, and then all of a sudden it's 8.45 degrees, and then 75.5 degrees, 87.8. So which reading is the outlier? Well, clearly this one. That's the outlier. Most of my days have been in the 80s or very close, like we get a 91 and we got a 79.5. So I'm pretty close together. And then this one temperature, this is like below freezing. So which we're reading as an outlier, if we said that. Is it an error? Or is it possible that it is correct? So I would probably guess it's an error. And partly that's because if you notice, all this data, we have one decimal point and then all of a sudden there's 2 decimal places. So most likely a decimal place moved. So the decimal place was probably recorded incorrectly. And like I said, a good way to get that idea of what it's going on is kind of look like at rest of your data. Everything here is the temperatures are rounded to a tens place, and then all of a sudden it's a hundreds place. That's a good indicator that there is a problem with the decimal point moving. So this is another one. The following represents the population of the 5 largest cities in the United States. Which reading is an outlier, and is the outlier an error, or is it possible that it is correct? So yeah, San Antonio is not going to be in here because I think it's 9th largest in the U.S. But we see we got Phoenix here with 1.7 million people. And then you have Houston with 2.4, Chicago with 2.7, Los Angeles with 4.1, and all of a sudden New York is 8.6. So you notice everything is rounded to the tens place. And this data it's significantly larger than Los Angeles. But like I said, the rounding seems to be consistent, so consistent decimals. So this is definitely an outlier, but I think it is correct. It is significantly larger than the other cities, but there's no indication that, like there was something with the decimal place being moved or something was recorded incorrectly. Okay, so one more thing that we need to add is something called an interquartile range. So one method for detecting outliers involves a measure called the interquartile range. The interquartile range is found by subtracting your first quartile from the third quartile. So if you're looking for this interquartile range, it's Q3 minus Q1. And what it is like, it's kind of like, with range when you did standard deviations. So this is like a measure of spread. Once again, it's just a measure of spread that's representing like 50% of your data in this, where it's, the center of it. So it is a measure of spread. But how we use it is going to tell us where there's going to be outliers. So most frequent method used for detecting outliers in a data set is our interquartile range method. So sometimes the namings of this vary a little bit, but we are going to find the first quartile and the third quartile. The rest of the data is not as important. It's just those two quartiles. So when you're looking at a data set, we want the Q1, we want the Q3. Our outliers could be like out here in our data set. So, but we're considering this to sort of be like the normal range. And so we're going to expand that and go, how far from that range in the center is too far out? So we're going to compute our interquartile range. So this is my interquartile range. Then we're going to compute the outlier boundaries. So these boundaries are the cutoff point for determining outliers. So I'm going to rewrite this data just a little bit, or my little picture. So make my data very, very spread out. So let's say this Q1 and Q3 is here. We want to know where these outliers start. What we're going to do is we're going to take that interquartile range and we're going to multiply it by 1.5. And what we're going to do is we're going to take that first quartile and subtract 1.5 times that interquartile range. So that could be like out to here. And this would be your lower outer boundary. So if I had a value that appeared out here, that would be an outlier. We have an upper outlier boundary. So that's going to be your Q3, because we're looking on the other side of that range that's considered normal. We're going to look at that Q3 and then add 1.5 times the interquartile range. So that could be like out here. So that's your upper outlier boundary. And if I have values that pop out here, they would be outliers. Our data isn't always going to have outliers. You could have outliers are all on one side or all on the other side. You can have outliers on both sides. You can have no outliers. So there's no expectation of where to find outliers. It's just we know it's going to be outside this boundary because this is how we define an outlier. So a data value that is less than the lower outer boundary or greater than the upper outer boundary is considered to be an outlier. So the following table presents the number of students absent in a middle school for each day in January, and we want to identify any outliers. So fortunately, this was ran through one of our stats. So we have our Q1 and our Q3. So Q1 is 45 and Q3 is 59. Represents the number of students absent. This must be pretty good size middle school. Anyways, your interquartile range is your Q3 minus your Q1. So that's going to be the 59 minus the 45, and that will be 14. Okay. So usually they're going to come out much messier than this one here. So what we need to do is we need to find our lower outlier boundary. And remember, this data is not in order, so we can't look at it and kind of see what the boundaries are. Our outer outlier boundary, so we are going to take Q1 minus 1.5 times that inner quartile range. So that is going to be 45 minus 1.5 times 14, which is my inner quartile range, which is going to be 45 minus 21, which is going to be 26. So anything less than 26 is an outlier. So if you look at your data, well, for one thing, the minimum is 41, so we definitely don't have an outlier here. So we have no outliers that are less than that lower boundary, like I said, lower outlier boundary. Now, if we look at my upper outlier boundary, try to make everything Q's now. That's going to be the Q3 minus 1.5 times the inner quartile range. So Q3 was 59, but this time we're going to add 1.5 plus, didn't get my plus there. So Q3 plus 1.5 times inner quartile range, so 59 plus 1.5 times 14. So this is going to be 29, or sorry, 59 plus 21, which will be, I believe, just 80. 70, 60, 70, yep, just 80. So anything greater than 80 is an outlier. So like I said, it's pretty common to have outliers just on one side of our data. But we see here, this would end up being an outlier. 77 is just small enough not to be. But anything that we found over 80 would be an outlier. And we have this one day where everybody was absent. So that's probably a result of an error, I would assume, because I can't imagine a whole middle school having everybody gone or absent, unless it's, like I said, that's probably some sort of error in that case. Okay. So you're just finding the boundaries, and if you happen to find outliers, you find outliers, but you're going to look for the upper and lower boundaries and determine if the data set has any outliers. So hopefully you still have your outliers. I mean, your outliers, you're a Q1 and your Q1 and your Q3. So this is more like what you're going to see, because this is going to be kind of messy. But my Q1 was 19.15. My Q3 was 30.95. So if we look for my lower outlier boundary, it is going to be, like I said before, the Q1 minus 1.5 times inner quartile range. And our upper outlier boundary is going to be Q3 plus 1.5 times my inner quartile range. Inner quartile range, the reason we need Q3 and Q1 is because those are the only things we need to calculate it. So this is going to be your 30.95 minus your 19.15. Oop, 19.15. And we end up with 11.8. So when I look for my Q1, not Q1, so my lower outlier boundary, my Q1 was the 19.15, and we're going to subtract 1.5 times that interquartile range of 11.8. 19.15 minus 1.5 times 11.8. And we are going to get a 1.45. So sometimes you might end up something with like negative that doesn't make sense. Also, spider the size doesn't really make sense. So it's pretty common to get weird values when you do this because sometimes this data is very skewed. If we're looking for my upper outlier boundary, then we need the Q3, which is 30.95. And then we're going to add 1.5 times that interquartile range of 11.8. So my 30.95 plus, and this is going to be, I think we don't have an outlier here, 36.85. So my data fits within the bounds. This case, there's no outlier. So like I said, sometimes you just don't have any. This value here is pretty close to being an outlier, but just small enough not to be. So one of the things that could happen is sometimes that 1.5 is adjusted. It's not always set to 1.5 to figure out your lower outlier boundary, your upper outlier boundary. This is kind of like a go-to value. We use a lot of go-to values for things, especially at this level of statistics. Like if we don't know what to pick for something, like when we do hypothesis testing, we're looking for alphas, it's always 5%. Here, when we're trying to figure out these outliers, we always use this 1.5. But it could be easy as 1, it could be 0.9, it could be there could be a little variation into that, this value right here.